Yeah. Okay. So yeah, apologies for yesterday. This hopefully things are back on track more or less. I'm certainly still pretty far from 100%, so I might be a bit slow and less interactive, but we'll power through. We'll essentially just get back to what we were supposed to do yesterday. So. As a quick reminder, on Tuesday we started looking at the problem from the perspective of a single particle. Today we're going to talk about various aspects of flows wherein we have many particles, and so we'll start thinking about concepts like volume fraction, number density, things of the sort. We'll start talking about concepts like clustering. We will start discussing, things of the sort, essentially. So that's going to be the morning. In the afternoon, we're going to switch gear a little bit. I'll introduce fairly rapidly the concept of Euler-Euler modeling. So we'll go through probably the simplest type of Eulerian modeling for a particle phase that one can think of. So we'll do a little bit of theory, but briefly, and then we'll talk about the resulting set of equations that would make sense to solve in a Eulerian framework for an ensemble of particles. And then we'll look at the implementation of that. We'll run essentially a couple of simple tests of the resulting algorithm, and I'll try to point out a couple of things. We'll see what this type of algorithm can get, and I'll try to highlight also what this type of algorithm cannot get. Okay, so this is going to be the plan for today. Tomorrow we'll get significantly deeper in the specifics. Okay. All right, hopefully that will do it. Should be good. All right, so tomorrow we'll go quite a bit deeper in the specifics of what it means to do two-way coupled simulations. I think it should be good. Thank you. So we'll go back to a Lagrangian framework tomorrow, and we'll look at what it really means to couple the phases tightly. All right, that's kind of the plan, and then on the last day, so on Saturday, we will be looking at what's missing, and I'll show you some more recent research activity that's been going on in my group, and I'll tell you a bit about what's the number of aspects that could be called state-of-the-art regarding particle-laden turbulent flows. All right, we'll kind of follow the same thing. So this is part of a significantly longer class, a full semester class. We're going to skip a few things and go directly to some of the things that I want to talk to you about. Oh, well, before we do that, I want to highlight that some of what we're going to talk about is discussed in details in especially this publication by Shankar Subramaniam from Iowa State University regarding what it means to think about a spray or an ensemble of particles as a point process. So we'll talk about that in some details, but not an enormous amount of detail. So I'll show you a naive way of thinking about what a suspension of particles might mean mathematically, and then we'll talk about what we would ideally need to do instead in order to make things more grounded in mathematics. So I'll refer to that paper a little bit later. If you're interested, I encourage you to take a look. Okay, so I'll start with some very basic observation that should not be new to really any of you, but that's something we don't typically think about, especially in the context of CFD. So we want to characterize a dispersed two-phase flow, and to do that, inherently, it is natural to introduce the concept of some sort of a volume filter. I will make this argument first from the perspective of single-phase flow. If you have a single-phase flow, one thing that you want to talk about is going to be the density of your fluid. Well, to define the density of the fluid, you need to make some sort of an approximation, some sort of a, you have to introduce some sort of a definition that allows you to express what the density is. A very naive way of thinking about that is to think of, mentally imagine an experiment wherein you scoop out a little chunk of the fluid and you weigh it, and then basically you take the mass that you've obtained in this measurement and divide it by the volume of your little scoop. That gives you your density. Okay, that's a concept that's fine, but you can imagine that it is a concept that is not independent of the size of the scoop that you choose. If you have a very large scoop, you might get a different answer than if you have a very small scoop. So the density of our carrier fluid, the surrounding fluid, if you report it as a function of the little delta V, the volume over which you're probing what the density is, you would expect two types of things to happen. You would expect, at very small scales, to have not enough molecules to sample in a way that's statistically relevant the composition in your fluid. And so you would expect to see oscillations. In the same way, once you get to very large scales, scales are comparable with your system. Say, for example, you're looking at a combustion problem. Your density varies by maybe a factor of 7 or 10 or something like that as you go through the flame. If your averaging region is larger than, if it encompasses both unburnt and burned gases, in the same way you'll start seeing fluctuations at the large scales. The hope, at least the inherent assumption that we're working with when we do CFD and when we do continuum representations of fluid mechanics, is that there's an entire range of probe size over which the density measurement is essentially independent of the probe volume. I should have clarified that you should think of this as a log scale plot. I'm not, we're looking here at orders of magnitude changes. Okay, so the argument I'm making here is that we're going to have both microscopic or micro scale fluctuations and macro scale fluctuations. Or uncertainty, if you will, which you will see once you go below essentially the characteristic length scale. That's the mean free path, as on the lower end. I'm calling here lambda the mean free path. And as you go towards your system scale, say big L is a system scale, you're going to start seeing also fluctuations. Okay? That's kind of something we don't think about that much because we're used to considering that this is the true density and we never ask ourselves whether there's any assumption behind this idea of a true density. Well, the reason why we typically don't ask ourselves that question is because if you're going to use the Navier-Stokes equation and use typical CFD tools, there's going to be a significant separation between those two scales. This is coming back to a Knudsen number assumption. We're basically requiring our fluid to be well represented by a continuum assumption, and therefore we require that there's a big difference between lambda and L. Okay, so this is just part of an underlying assumption that we typically make. Well, what we're going to have to think about particles, we're going to do essentially the same thing. Or at least this is one approach that we can use to start thinking about a population of particles. So here we were working with, not particles, we were working with molecules. The molecules that represent, are the collection of molecules that is our fluid, whether it's gas or liquid. Now, we're going to shift our focus and think about what this means from the perspective of particles. If you have a collection of particles, well, you can say something meaningful about the density in particles, either volume density or mass density or a number density, provided that you can guarantee that you have more, sufficient sample of particles within your volume of interest, but that this volume of interest remains small compared to the relevant scales over which you expect things to change because of the fluid dynamics. So essentially, the problem we're going to be facing is that it's going to be difficult for us for particle-laden flow to make an assumption of what is the particle Knudsen number. One thing that's obvious here that I might as well mention, we're not talking about the density of the particle phase. This is not an issue. The particle phase is going to be either liquid or solid or gas. It doesn't really matter, but typically the particle itself is going to be much larger than the intermolecular length scale of the material that forms this particle. So we're not concerned with how to calculate the density in the sense mass over volume of the material that makes up the particle. So if this is my particle of diameter d, I have no problem obtaining, from the same assumption as above, a corresponding rho droplet at that location and at that time for my solid particle, because it is going to be completely, the intermolecular length scales are going to be much smaller than d. By the way, this is not always true. If you're interested in soot particles, for example, well, the size of the soot particles might be small enough that you're kind of getting back to facing this problem. Your soot particle might be a collection of a sufficiently small number of molecules that defining its density is not that straightforward. So it's in general solid and liquid particles. Your diameter is much larger than the mean free path. So rho of the drop of the particle is well defined. Okay, so this is not our concern. Our concern is if I want to count the number of particles, if I want to say something about my number density locally in my particle field, this is where I'm going to have to be a little bit more careful. So let's talk about the concept of number density. Ideally, and the same idea of scooping out a chunk of fluid and weighing it and deriving a density from it, we can do the same thing with the concept of number density. I can scoop out a region of my flow, and then I can count the number of particles in that region, divide by the volume. That tells me the number of particles per unit volume, and that gives me what we're going to call a number density. So this is all fine and good. That gives me an n number density, the function of space and time, which would be, well, an effective number delta n particles divided by an effective volume size delta V volume right here. The issue is this. So, in terms of units, this is just number of particles per meter cubed. So this is fine and good. The issue is that now we need to ask ourselves, what should that volume be? Well, if that volume is too small, or not, you can imagine if I were to consider a volume here of that size, I would simply miss all the particles, and I would conclude that my volume fraction is 0. If I were to look at an averaging volume that's as big as my system, I would make this measure essentially useless. At least I would have no local information. So the assumption here is that there is a reasonable range of scales somewhere in between our interparticle length scale and our system length scale, over which I can reasonably hope to define this averaging volume. If that separation of length scale exists, meaning if that Knudsen number, if we can define a particle Knudsen number that is that allows us to make some sort of an assumption of a continuum for a fluid, for a particle, then this is fine. So the assumption here is that we're going to let our averaging volume tend to some sort of a small but not too small volume size, delta V naught. That leads to the question, how should we choose delta V naught? And so we need delta V naught to the power 1/3 to still be larger than the interparticle distance, and we need delta V naught to the 1/3 power to be ideally much less than the system size. So that requires a separation of scales. So this is not a completely, it is not a subtle assumption. And I'll give you just one example of a situation where we might struggle with this. We'll go through more concrete flow examples. Yes, sorry, go ahead.
As you can see, there is a particle which are only some portion of that in that control volume. So should we consider those particles in this, or we should only bother about the center of particles at the particle?
Oh, you're saying, what about those particles that are at the edge? Is that what you're saying? It's mostly relevant to our discussion. Different frameworks will do different things. Yeah, different frameworks will do different things. It's your choice to make. It doesn't really change the story. We're more working at the level of the conceptual thinking here. So the point I wanted to make is that imagine a fluidized bed reactor. So a system where you have a packed bed of sand in a vertical tube, and you inject gas from the bottom. What's going to happen in the system is that the sand will become fluidized, so the particles are going to start floating around and bouncing around. And at the surface, well, there's going to be bubbles rising in the system, and I'll show you movies of things like that in a couple of days. Those bubbles are going to burst at the surface and then send particles flying above the bed. So really what's going to happen is you're going to have a packed region of bed wherein the particles are very close to one another. Okay? And in that region, it is not going to be difficult to find a length scale that is in between the interparticle distance and the system size. Above the bed, the particles are going to be very, the distribution of particles is going to be very dilute. And there it's going to become a lot more challenging to think about. Well, basically what I'm saying is the interparticle distance is going to become large. And then suddenly the concept of this averaging volume becomes very problematic. Okay, we'll ignore that for a second, and then we'll go back to this from the perspective of proper statistical considerations. Once you have the number density, obviously, you can extract from that the volume fraction. So instead of counting the particles, you can count the volume. So you can define from that your dispersed phase volume fraction. Which will be in this case, say alpha d, which would be now the limit as we go to this appropriate delta V naught volume of the volume contained in the particle over the probe volume. So down, this is a dimensionless quantity. This is in meter cubed per meter cubed. This is the volume in the particle over the volume of the probing region. So we'll make extensive use of this. And then, obviously, I can do the same thing with the carrier phase. The carrier phase will be the surrounding fluid. And that's simply going to be 1 minus alpha d. Obviously, if I have only particles or carrier, the sum of the two needs to account for 100% of my volume. Okay, so now let's think a little bit about how we resolve this problem of having to require the separation of length scale. What we've done here so far is we've relied on this concept of a local volume averaging. It is going to be very convenient to do, and in all honesty, so tomorrow morning, this is the concept we're going to use in order to help us derive a very nice set of two-way coupled Euler-Lagrange equations. Okay, so we're going to make use of this. And I'll try to show you the next day that it actually works really well, even in situations where we don't really have the scale separation. But still, conceptually, this is not a particularly desirable situation. That basically we can't define this proper, we can't always rely on this proper separation of length scale. Well, I imagine you've all been exposed in one way or another to the concept of Reynolds average Navier-Stokes equations. We can use the same type of idea here and start thinking about ensemble averaging instead of volume averaging. That solves this problem, but at a cost that essentially makes it incredibly impractical from the perspective of detailed simulations. So that's going to be an interesting trade-off. I'll just introduce the concept here. Basically, the argument is if you don't have scale separation, you cannot rely on volume averaging, or at least you cannot rely in a practical way on volume averaging, or at least that would be the argument. I'll show you that this is not necessarily true. But ensemble averaging is always going to be available to you. And essentially what we're saying here is that as long as you have a random process going on, you can always define the mathematical expectation. It doesn't matter how you get it, but you can always rely on the properly defined, say, estimate from a number of trials. So for many trials or realizations. So, sorry, I removed that as soon as we can do a couple of simple examples, but it's not particularly exciting. This is something that should be clear. If I toss a coin n times, I can get the probability of the outcome being equal to head, say, and I'm going to call this probability P sub h for head. Now I can build an estimator for pH, and this is going to be the number of times I've obtained the outcome head over n, and this is my very standard ensemble averaging. So with this, the properly defined mathematical expectation will be the limit as n goes to plus infinity of this estimator based on ensemble averaging, which I would certainly hope that in most circumstances would be 0.5. Okay, so this is something that's not particularly magical, but you can already the issue. You have to run multiple trials. So basically we're saying, if we consider the distribution of particles in our set of particles is now a statistical problem. And basically we're saying that we can look at the same fluidized bed many times over, where every time we're looking at it, there's the same exact physics, the same exact process, but with a different distribution of particles. Now, if we average locally over the realization and count whether we have, basically decide whether we have a particle or not at our location, now we can get another kind of estimate of whether, of the number density of particles. So we can just say, at a given point, for how many of my realizations did I actually have a particle at that location? That divided by the number of realizations gives me an alternative way that is always properly defined of obtaining a number density. Computationally, now this is tricky. This is not an easy thing to do, because the idea of doing multiple trials is completely fine provided you have a one-way coupled problem. So if I have a flow in which I'm tracking particles, but the particles don't influence the surrounding fluid, it's fine. I can run many independent particle calculations and get an answer regarding what is the number density. Now, if the particles are influencing the fluid phase, this is a lot more tricky, because now each of these independent trials would lead to a different flow field, and therefore those trials would lead to diverging realizations that would not be an appropriate representation of, or wouldn't give us an appropriate ensemble. So it's a pretty tricky problem from a pure CFD standpoint, and that's why we're going to mostly end up staying away from it. So I'll add a few things here. I mean, I had another example here, but I think we can skip this. But the big idea is that if you want to have a properly grounded, always applicable theory for multiphase flows, you do want to make use of a proper concept of mathematical expectation. So I'll concede that point. So general theory of multiphase flows that uses average concepts should be based on a proper mathematical expectation. This is what will require the fewest number of assumptions. So concretely for our problem, that means that we would ensemble average over a number of realization. I'm going to draw a, so say this is our domain of interest. I'm going to put particles in there. Now the two competing ways we have to think about volume fraction. One was to try to draw or look at an area at a volume in this and count the number of particles. Now we're going to say at a point, or basically over an infinitesimal volume, which is now allowed to go to 0, I can count the number of particles. That's going to give me my number density as before. But now I'm going to want to let this delta V go to 0, and I'm going to rely on the fact that I have access to multiple realizations. So realization 1 and now for those different realizations, the particles are going to be located differently, randomly. And now at my infinitesimal probing volume, I will either have a particle or not. And so now we are truly free to let delta V go to 0, and therefore we don't have to make any assumption regarding scale separation. So ideally, this is what we would like to use. Here I said also that this is only if your theory of multiphase flows is using average concepts. Well, I'll give you an example of where you wouldn't need that. Say you're doing particle resolved direct numerical simulation. You're solving for the entire flow around even the individual particles. In a situation like that, you do not need to rely on any type of averaging concept. But in pretty much any other situation, if you're interested in the question of what is my local density in particles, right? I mean, either number density or volume density in particles, you will have to have some sort of an averaging, you will have to go through some sort of averaging exercise. Yeah.
How are you calculating the number of particles in a particular volume in case of a number density? Similarly, in the volume fraction, how are we calculating the size of a particle? Although it will be varying.
It would be varying. What do you mean?
Means the size of a particle cannot be the same every time. In a particular volume, the size can be of different size.
Right, but the presumption here is that you would be solving for it in some way, so you know the size.
Suppose in case of a drop.
So what is the size?
Number density is the number of particles, but in case of volume fraction, there is the size of particle that matters.
Right, so if you give yourself an ensemble of particles of known size, then you know the size. If you give yourself an ensemble of evaporating drops, then the size would come from the solution of the set of equations we talked about 2 days ago now, accounting for evaporation. So when you solve for the evolution of the temperature of the drop and the evolution of the mass of the drop, well, the mass of the drop, assuming the density of the drop, will give you directly the size of the drop. So you would need to solve dynamically for that size, but the assumption is in a fully closed CFD model of this problem, you would have already this size available, right? Because you've solved for it either from ODEs or from a Eulerian version of this process. Does that make sense? Yeah.
Can we go for temporal averaging then?
Yeah. So this is an interesting concept. There's instances where it is possible to go through temporal averaging, but conceptually you have to be careful. So obviously you can build a mathematical estimator from a temporal average, provided that the process you're looking at is stationary. So it is fine conceptually. Now the issue is, it depends what type of approach you're using. So if you're using something where the fluid is already averaged in time as well, so basically if you're using a Reynolds average Navier-Stokes approach, then yes, provided your problem is stationary, this is fine. This should be fine. If now you're looking at more detailed simulations where the fluid is not Reynolds averaged, then you're back to the problem of ensemble averaging. How do you do a time-accurate simulation that depends on knowledge regarding the volume fraction if you first need to have done that simulation in the first place in order to get this number density. Okay? So it is fine provided that you give up any type of time dependence is basically what I'm saying.
Can I go for when I run my particular, not a Reynolds average equation, I will simply solve my instantaneous Reynolds equation, but I will reach for a statistical steady state, and then I can go for my ensemble average.
Say that again, please. So you're saying?
I will search for my statistical stationary state and my kinetic energy of the fluid or particle, which is a statistical stationary state with respect to time. Then I can go for my ensemble average.
Well, but again, the question is if the phases are coupled, right? So if the phases are fully coupled, then through that coupling, they will, the coupling will involve quantities like volume fraction. And we saw that 2 days ago. There was this mass loading concept that showed up in our source term for drag in our Navier-Stokes equation. So this shows up in your instantaneous calculation. So there's a problem here of what comes first, or how do you get a volume fraction necessary to run the coupled simulation if you don't already have ensemble average data. So conceptually, it's problematic. And you don't see those type of the use of ensemble averaging for particle-laden flows has not been particularly extensive because conceptually it's tricky to implement in the context of CFD. Are there other questions? Okay, so I was redefining a number of things that I think are not. So we're going to skip some of that, and I'm going to go to. I'll make a few comments on polydispersity, and then we'll start talking about a number of aspects of. First, the importance of thinking about inhomogeneity in the distribution of particles. We'll talk about the concept of loading, and then we'll start talking a bit about the concept of clustering. So polydispersity is something I'm going to touch upon pretty from a more pragmatic standpoint. And we're talking about that. The particle diameter might be unknown, or might be changing, or might come from a non-trivial distribution. So in a general sense, if you're thinking about this problem as a statistical problem, the position of the particle will be a random variable. Now we're saying that the diameter of the particle should be also a random variable. So if for particle I have a diameter d of I, that might be a function of t, that will give me as a set of random variables I'll be working with the position of particle I as a function of time, and the diameter of particle I for I is equal to 1 all the way up to the number of particles, which could also be a function of time. That's our set of random variables. So it's pretty classical to start thinking about that from the perspective of probability density functions. So we can introduce a probability density function of position, time, and in this case diameter, that describes, so here this little d, that's my sample space variable that corresponds to big D. So this is my space of possible diameters over which I'm interested in the probability density function. So from a probability standpoint, I have a certain probability of finding a particle at a certain location. On top of that, I have a certain probability of that particle being of a certain diameter. That's basically what we're saying. We'll be extending that this afternoon with this concept of the fact that the particle locally has a certain probability of having a certain velocity. Right? So that we'll keep on adding on to that probability density function representation. A pretty natural way to write this we can write this probability density function as the product. Oh, well, this is where of what is already a probability density function from the perspective of position. So if I ask myself, what is my probability of finding a particle at a certain location? Well, that's what we've defined before as this number density. So n of x and t is already the so this is my probability density. This is my number density. Therefore, this is the probability of finding any particle at x and t. Okay? Now, I'm adding to this another variable, so I can multiply this by the conditional distribution that represents the size. So I'll naively write that. So this is going to be a conditional. So given the number of the probability of finding a particle at that location, what is the probability of that particle being of diameter d? So we're going to classically decouple those two questions. We're going to have a certain probability of finding a certain size of particle, and then we're going to have just the probability of finding a particle at all at a given location. So now that leaves us with this f, the conditional as really just the, and to be clear, I'm making this still a function of position and time, because this probability of finding a certain size of particle will be a function of where we are. Imagine you're looking at an evaporation process for spray going through a flame. You would have a higher probability of finding bigger particles if you're far away from the flame than if you're right at the location of the flame. So this will be still evolving in space and time. So this is now our PDF probability density function of the particle diameter. And you'll want this to be normalized, so such that the probability of finding a given diameter, once you integrate it over all possible diameters at that location, comes down. So that's, well, it's going to be d of d, sorry, is equal to 1. We'll make a little aside here to talk about the characteristic diameter. What am I writing? Characteristic diameter. if you have a distribution of sizes, it makes a lot of sense to simply care about the mean diameter. Say d sub m. You can ask yourself what is the median diameter. Those are all pretty naive statements. Experimentally, so the median here would be the value up to which you would have to integrate your distribution in order to get one half. The reason I'm talking about this is because experimentally it's very tricky to calculate this. If you're looking at sand and you can manipulate it, you can sift it, you can obtain a distribution of sizes, you can generate those quantities. If you're looking at the spray, good luck sifting your spray particles. So you're not going to be able to do this. Instead, what you're going to be able to do is get some measurement of the normal density, potentially some measurement of the volume fraction. You know, the shadow graphs and light extinction type of data can tell you something about the volume occupied by the particles. And you can get also some information regarding the surface area of the droplets. So you can look at surface occupied by the liquid. So what is, in the end, a lot easier to do is look at the volume of the local volume, the total volume in the particles, and look at the total surface area of the particles. You can do that as projected surface area and then recover from that a total surface area. So what ends up being easy to measure is what is the mean surface area, what is the mean volume. So we're going to be looking at ratios of moments of that distribution. We'll write that as a d m k will be the ratio of the mth order moment of that distribution, moment in diameter, to the kth order moment in that distribution. So 0 to infinity, we'll look at d to the power m of f d divided by the kth order moment. We want this to have the dimension of a diameter, and so we'll divide that by 1 over m minus k. So that's a general definition from the moments of what a reasonable estimate of characteristic size might be. Specifically, like I was saying, experimentally, you'll have access to the second and the third order moments typically more easily. And as a result, what you'll often find is the concept of Sauter mean diameter. The Sauter mean diameter, SMD, is, according to that definition, D32. Okay? I'll add a few things, but not too much on this. Essentially, I'll point out that essentially approaches wherein you solve for the particle diameter, or approaches wherein you assume the distribution of particle diameter. When people assume the distribution of particle diameter, that's fairly typical laws that are used. In the general sense, if you have a random process that generates an unbounded variable, nature typically makes it such that a Gaussian distribution will probably be a decent model. If you have a variable that's bounded on one end, say bounded at 0, and unbounded on the other end, it's often found that the log normal distribution will be a very classical observed distribution. While the particle diameter is by definition going to be larger than 0, and therefore you can expect that if your particle distribution has come from an evaporation process, an atomization process, or a fragmentation process, you'll probably get a distribution that will not be too different from a log normal distribution. I'll show you in a couple of days how this log normal distribution shows up in a number of other situations as well. So if you gave yourself a variance of the log of d, and you give yourself a mean, that gives you something like this. The problem with this is that it's not very easy to parameterize. You have only 2 parameters that don't give you a lot of flexibility, especially if you know the mean size. Basically, you can't really reshape the distribution that well. People doing sprays, I've worked a lot with what's called the Rosen-Ramler distribution. That's been found to be more easily tunable to represent spray drop sizes. That seems to work fairly well. So it's purely empirical. There's no physics behind that. With a parameter delta and n, what you do is just yeah, it's usually written not in terms of the. Sorry, we're gonna write the. I'm gonna put an uppercase F. It's gonna be the cumulative distribution function, not the probability distribution function. So this is now the CDF cumulative. So it's the primitive integral of the size PDF. Okay. We could spend a lot of time talking about how Eulerian methods deal with sizes. It's something that I think goes a little bit outside of the scope of our discussion. In terms of Lagrangian methods, we've kind of discussed that already. If you're solving for the temperature and the mass of your particle or your drop, then you already on the fly are solving for the size distribution in the Lagrangian framework. Even though we didn't do that in our little code, and we will not do that. Okay. Next step, we're going to talk about mass loading into particle spacing. How to distribute particles, the different type of homogeneities that can be expected. We'll make a few observations regarding the importance of knowing something about the variance in the number density, and then we'll start talking about processes that can lead to non-uniformity in the particle distribution. So we'll talk about clustering. If you're okay with this, we'll take a little break, say about 10 minutes, and we'll reconvene at 10:40 or a little bit before 10:40, and resume. All right. Yes. Oh, sorry. I thought you had a question. All right. Thank you.